It's a little bit provocative title because yeah, it refers to the 3 laws of robotics that are really famous for the science fiction. So the laws is to protect humans, to obey humans subject to the previous law, and to protect itself subject to the 2 previous laws. These laws are rubbish. Actually, even Asimov, who made these laws, the point of these laws is of his work is to show that these kind of rules cannot work. So it's more like philosophical thing. But I like the idea of having the laws. So I want to make my own laws. If we have robots that is subjected to unexpected forces, my 3 laws, which have also priority, are that if an unexpected force happen, we need to detect it, identify it, and control it. Especially if we think that, I mean, in the context where there might be humans around. So that's the first rule. The second one is to avoid failure and to recover, subject to the previous one, because the safety is more important. And the third one is to try to achieve the task anyway, and that's like the least priority. But if we can achieve it, it means that we have completely rejected the disturbance. So for our case, I will talk about our robots which have no torque sensor. So I'll present like a couple of methods that suits our robots. I think they can extend to robots that have torque feedback quite easily, which could maybe even increase the performances. Yeah, for every step, for every law, there is like a different loop, I could say, like the detection, the control of the forces, the recovery, and the task achievement have their own control loops. I will not present full solutions for that. I don't think that exists yet. I will present some estimation method here for the detection and identification of the forces. Some estimation in the case of highly dynamic motion, and the closed loop control that allows to achieve the task subject to the disturbances. So for the first one, I want to talk about a paper that we did like a couple of years ago about experimental evaluation of simple estimators of humanoid robots. And the word simple was like really important in this paper because in that one we were mostly comparing kinematic estimators that uses IMU encoders, maybe contact information, but it stays at the kinematic level. But I have developed also a dynamics estimator, and I think this one is the one that I will talk about today. The thing is that this estimator with the complex dynamics was producing higher errors than simpler one, even if it was computationally more costly. So it's not like much higher, like just more millimeters, but yeah, the simplest one were giving like bigger, smaller errors in the kinematics estimation. So yeah, I'm not happy about that, but I think I can improve it, but it's not the point. What I want to present is I still would promote it even if it were the case, because being accurate or precise is not enough to guarantee the quality of the closed loop control, especially in nonlinear dynamics. In linear dynamics, we have the separation principle where we could separate the estimation and the control. In nonlinear control, you need to deal with closed loop dynamics, which is not necessarily stable, even if the estimation and control are stable independently. So yeah, more properties like stability and smoothness, and maybe not being too sensitive to errors that are necessary to guarantee the quality of closed loop control. Also, with the kind of kinematic estimators that we have here, we usually build different estimations and that are inconsistent. So we have estimations of the forces, we have estimation of the kinematics, we have sometimes estimation of the absolute position during using SLAM, and they are not consistent each with other. And actually, they are living in different control loops. Sometimes the kinematics corrects for SLAM, but I haven't seen many times that SLAM correcting the kinematics. And I think that's something that's weird because we have just one single system, so we should have one single state. So that means that we have to refine the model and to be able to rebuild the same state, given all the measurements that we are having. And the last point, which is the most important in this talk, is that some variables are only observable with a rich model. So here I present the estimator that I developed through several publications. And so it's one state estimator, single state estimator that takes all the available measurements on our robot and builds floating base kinematics. And it gives also contact force information if they are not available with force sensor. We have even shown that we can stabilize the robot using this feedback without the force sensors. And in 2018, I have shown that we can get also other external forces that are not measured, that are not modeled, that are not contact forces. So the idea, I mean, the experiment was to ask the robot to perform a task with its hand. So its hand has a force sensor, but we don't use it. So we just ask this estimator to get the estimation of the forces, and we use the force sensor of the hand as a ground truth. And you can see that we are able to rebuild the forces and the moments of this contact, this external force, rather accurately, especially in the forces, maybe a little bit less in the moment, just using the IMU, the force sensor at the ankles, and the encoders. And here we show that we can even build an axis that goes not, I mean, I can rebuild the axis that is the closest to the contact, given these measurements. And this axis goes like 7 centimeters, has 7 centimeters of error between the contact point and this estimation. So we can get also information on the application point using this estimator. Of course, it is limited because it will only give you the force of one contact, I mean, the resulting external force. So if you have two contacts or two forces, it will not be able to distinguish them. But the point is, we can simply see it as transforming the whole robot into a giant force torque sensor. And this is possible thanks to a model-rich estimator that is able to not only use the redundancy that lies between the force sensors and the kinematics, because the force sensors will give the forces and the forces will give the accelerations of the center of mass. So there is redundancy between the force sensor and the kinematic. Not only it deals with that, but also it's able to have new observable states thanks to this coupling. So yeah, this work is being extended. So it's been a couple of years that I haven't worked on it, but I think that we can improve it with more efficient implementation, better integration with absolute position and torque sensors, odometry, etc. But I think you would be right by saying that the precision is important. Actually, I'm not saying it's not important. So precision is important. And in the case of our observer, it relies a lot. I mean, the observer relies a lot on the dynamic model. So if the model is wrong, and the precision will be lower, and the modeling error will show up more in dynamic motions. So I think that's right. So that's why I will present another kind of estimation framework for the case of dynamic motion And I put it here because that's usually the context where we need to avoid failure, at least for humanoid robot, where we need to recover balance. This is another estimator. So it's the idea is to consider, just let's suppose we know what is the fixed point of the robot. With the fixed point, the instant fixed point is at each instant what point of the robot, or even not really in the robot, could be like between the feet, what point in the frame of the robot is not moving, it has zero velocity. So usually it's around the contact points. We can consider, for example, the ZMP. So ZMP could be considered as the fixed point. If we know the fixed point, so just using the IMU, the encoders, and the joint velocity, we can rebuild the linear velocity in the world frame expressed in the local frame. So let me call it x1. And let me call x2 the direction of the gravity in the local frame. So this is this gives a kind of roll pitch, like 2 degrees of freedom of the orientation. So the state dynamics is actually really simple. So S here is just the skew symmetric operator. So that's just the cross product. And I would define like a really simple state observer, that this is like 6 lines here, like six rows, like 3 rows, that are 3D vectors. So in code is just like 2 lines of code, these 2 lines of code. And with this estimator, let's build just the vector of error. And the vector of error has dynamics that looks a little bit complex, but if I change the variable by looking at the error in the global frame, I end up with this dynamics. So this dynamics is linear. So these are 3D vectors too. These are errors. So when it's 0, it means that we have a correct estimation. It's stable. So it's globally exponentially stable. It means it will go to 0. But what is important here is to see that it is autonomous. It means that it doesn't have any input. It only depends on the state, on the error itself. It means the error dynamics would be the same whatever the motion of the IMU. Whatever the IMU is doing, the estimation will converge in the same way to the correct one. So it could be any kind of dynamic motion, any kind of impact motion. So for example, here in simulation, we just make the robot, we make this robot, simulated robot, here oscillate, then we make it somewhere around here, we make it fall, and we follow like the vector of gravity in the local frame. So here we can see the fall. Here also we can see the fall. So X and Z component are showing the fall. Here there is like a big impact. And here I compare several estimators. So the one that I presented here is this one, the red. And we see that the error is actually really, really small. And during the fall, it doesn't increase a lot. I mean, it's maybe the same order of magnitude as the error during the oscillation. So this is because the fall was respecting the hypothesis that there is a fixed point that we know. So we just use the force sensor to get the ZMP, and with the ZMP we can rebuild the position of the fixed point. So of course it depends on this assumption. So if I don't know the fixed point, or if it's wrong, or if the robot is slipping, it would be less precise, but the error would be filtered because this estimation is going through a complementary filter. So if there is like a short slip, it will be filtered. And anyway, that's better than the other estimators that just consider fixed points or use the forces to predict slipping just to decrease the confidence that they have in the contact points. So yeah, we didn't make our robots fall, so we just I just show like some results in closed loop with this estimator. I mean, of course, it would work with it would work without issues. So in summary, so we just assume that there is a fixed point that allows to give us the linear velocity. Better noise filtering is obtained through this estimator. We have proven Lyapunov convergence, and to my knowledge, this is the only estimator that has proven Lyapunov convergence in humanoid robots. There are other estimators which have local convergence. This is a global convergence, so it's really strong guarantee, and the error is autonomous. So we are presenting also into a transactional automatic control a generalization of this estimator to the nth order filtering. Filtering. Which can increase the rejection of noise. So that's submitted currently. So now let's move to the third law, which is to try to investigate how we can achieve the task in the presence of these unexpected forces. So throughout several publications, we have presented the torque control approach that uses robots without torque feedback. So one key idea is to, so this is the reference acceleration coming from the QP. And we integrate it and get the error in velocity between the integral of this reference acceleration and the current velocity obtained from the robot. And this integral term allow us to correct for errors in the sorry, errors in the computed torque. So since we don't have torque feedback, we don't know what's the amount of friction. We don't know what's if the torque is actually achieved by the motors. So we correct it using this integral term. But it has even, I think it has interests even for torque feedback robots, because this kind of integral feedback gives a strong proof of convergence of the joint position. So S is the error in velocity. We know that S goes to 0 exponentially. But since S is computed through the reference acceleration that takes into account the position and the velocity, we can prove that this amounts at having the convergence of the integral of the joint position error. So it's not only the position error going to 0, but its integral is going to 0. And that's yeah, that's known to produce a bigger, I mean, higher robustness, and to give no static error, even in the case of modeling error in mass distribution or this kind of stuff. This is really strong. So the guarantee that the integral of the joint position error goes to 0 is strong, especially in the case that we are dealing with here, in the case where we have disturbances. So do we really want that? Actually, what we want is the convergence of one maybe specific or several specific tasks. And we have to acknowledge that integral terms can be dangerous. For example, if the robot hits the wall and there is like integral term, it would just try to break the wall. So we have submitted to IROS a series of safety measures, some anti-windup that is based on a QP that guarantees that the integral term will never exceed the given values. and it does it in an optimal way. So it doesn't, it only reduces the torque that is exceeding the value, but doesn't decrease the performances of other components of the motion. We have presented also some leaky integration scheme with the second order filter that allows to target specifically some kind of disturbances. So instead of using just simple integration, we can have a quick integration for stiction and really impulsive disturbances, and the slow integration that can deal with the modeling error. And finally, we presented the null space compliance that I will present here briefly. So the guarantees of convergence of the task can be improved just by changing a little bit the integral term. So instead of having just the integral term like this, we add also some terms that are related to the specific task that we want to achieve. So by doing that, we can guarantee the convergence of the integral of the acceleration error of the task. But similarly, since this comes from the QP, so the QP is aware of what is the desired one. So it means that we have the convergence of the integral of the task error itself. So for example, if I want, so if I want a 6D pose task, so the integral of the 6D pose error would be going to 0. And so that's really the same kind of proof of guarantees of convergence, but only on the tasks. So this allows us to make the remaining degrees of freedom compliant. So this is how we can demonstrate it. So this is our robot HRP5P, which has no torque feedback. So here it's on a stand. So the stand is not perfectly rigid. So when I say the hand is stiff, but actually you see it going down and up, it's mostly the stand that's moving. So here we are not, since we are applying really strong forces on the robot, we are not dealing with balance. We are just dealing with the task itself. So we put the robot on the stand. So here the task is really stiff, and also the null space is stiff. So if I activate null space compliance, I have the same property, like it's the same stiffness for the task. But now the null space of the task now is compliant. It's not really easy to move it, because this is a passive compliance, so I still have to deal with the friction. And it's a really high gear ratio robot. It's a really powerful robot. But what I want to show is that I can move degrees of freedom, and at the same time, the hand remains in place, even if I move the other degrees of freedom. So here the arm has 9 DOFs, and the task is the 6 DOF. So I have 3 DOFs of null space, but only 2 are easy to move. The third one is really complicated because we have a high friction and we don't have big leverage arm. And actually, we can also have fun and combine this with some admittance. So now we can have at the same time different compliance, either in the task space or in the null space. So here I can move the null space, and this remains in place, or I move the end effector itself, and it follows. So yeah, we can have fun and combine several kinds of controls. And so this this can be also used for. So this is like really recent result that we got. It's not even in the submission to IROS. We can use it for moving. So we can, like, the robot is asked here to perform some trajectory in the space, but there is there are vertical bars. So the robot is not aware of the bars. It has no measurement of the bars. It's completely blind. and it has no feedback of the presence of the bars, even if it touches them. But still, the robot is asked to do it, so it collides completely with the bars. But thanks to the compliance, it's able to reach the task. So it's not perfect, of course, because during the disturbance, the task error increases. But thanks to our control, we know that this task error will go back to zero quickly. So I can show you also the trajectories here. So this is the reference trajectory that is required here from the robot in the space. So this is x, z, and this is x, y, z, sorry, and this is x, z. Maybe here it's clearer. So this is x, y, z reference in blue, and the actual position in red. And we can see that, yeah, there is some errors here that happen just because of the disturbance, but the impact was compensated here, and the task could be achieved. And more importantly, we didn't break the robot, we didn't break the environment. And with this kind of robots, especially a Sharpie-5P, this is completely impossible with position control, except if we modify it in a really extensive way. So, sorry. So that's basically the methods I wanted to present. Of course, the control parts are a little bit missing in my presentations. We have been working on them in a few works. So here you can see work by Rafael Cisneros Lemon, where the robot in simulation hits the environment, but it's still able to keep balance and to reject it. And with Masaki Moroka, we are working on how to integrate. Oh, that's a mistake. How to use a measurement of how to say, if we can measure the error between the desired and the real forces, how can we include this measurement into the stabilization? So here there is different friction ratios between these areas, but there is a force sensor at the wrist, so we are using actively this data to correct for the stabilization. This has also results on the real robot, but yeah, so the paper is submitted in RAL. So if, I think it's about to be accepted to RAL. So yeah, please check it if you want to have more details. So thank you very much. I'm sorry for this maybe a short presentation, but yeah, that's it. There are still many missing bricks to achieve these laws, and yeah, I would be happy to discuss that with you.
So Mehdi, thank you very much for being with us despite the sickness. Hope you can recover soon.
Thank you.
Yes, the presentation is very impressive. I do learn a lot of missing details. I'm wondering that are there any questions from the audience? Well, if no one is willing to grab this opportunity, may I ask one point, Mehdi?
Yes, please.
Yes. So basically, I'm wondering that is it possible? I mean, according to your three levels of loss, I'm mostly working on the first level, that is detect, identify, and control the external forces. So I'm wondering that is it possible to estimate the external force without using a force torque sensor? I mean, only use encoders and IMUs.
Using only
encoders
and IMUs. Yes. Are you talking about humanoid robots?
Yes, because I noticed that some small size toy robots, they can kind of react to the external disturbance and perform kind of push recovery. So yes. I'm wondering that is it possible for humanoid to estimate external force using only encoders and IMUs?
So in the thank you very much. That's a really good question. So in the paper here ICRA 2018, I have presented also the case if there was no force sensor. So if there was an estimation, but it wasn't really good. The how to say, the force component was not really good, because with the IMUs it's not possible to get like you cannot get all the components of the external force. You can get moments that can deform the robot. So you mostly get 3 DOFs out of the 6 DOFs of the forces. So it is possible, but the quality is much lower. I don't know if I have here the results. I think I have them here. Where is it? So with the same experiment, can you see the paper?
Oh, yes.
So the same experiment, I also tried without the force sensors. Where is it? Yeah. So here we can get the force, 1 force and 2 moments. That's what I could get.
Okay. Yes. Great. Thank you for the answer. I will check the details in the paper in the future.
Yeah, please. And if you have questions, don't hesitate.
Yes. Maybe one more point is that you mentioned that the dynamics approach can produce bigger errors. So what could you, I mean, could you please briefly answer why is that? Where does uncertainty come from? Does it come from the uncertain dynamics model, or what?
So for that specific experiment, I know that the IMU had the gyro had some bias. So this allowed me to make my model more complex and to add the bias estimation, but this hasn't been released yet. So yeah, so what happens usually if I find a big error, it means that the model is wrong and it needs to be refined. So I think it's interesting also because it allows to have a nicer model, and the nicer model is a better predictor of the dynamics of the robot. So I have been using the models for estimation also for the control, and we have shown that the prediction is not that bad if you refine your model.
Okay. So we can maybe one of the possibility contributes from the uncertain models.
Yeah. So yeah, there is the uncertainty in the contact model is the biggest one. So I worked a lot on that, but there is still some modeling errors that need to be tackled.
Okay. So if there are no more questions from the audience, I would like to thank Mehdi again for the nice presentation and excellent experiments, and hope you can recover soon.
Thank you very much. Bye.
Bye.